Today we are doing 2.1, which is called using inductive reasoning and making conjectures. That's what it should say on your sheet. I don't think it should say. Okay, so you guys just read through this first paragraph. Now we're going to go over it together. And then hopefully you guys found some key things to highlight. So the first thing I did is I read through when several examples form a pattern. And I thought, okay, if it's forming a pattern, that's going to be something I need to know. And in addition to forming the pattern, you're going to assume that the pattern will continue. When you do that, you're applying inductive reasoning. Another example of inductive reasoning. If Michigan State is winning all their football games, okay, or the Hazlet Vikings are winning all their football games, then we would assume, based on inductive reasoning, that they were going to win on Friday night or Saturday night, right? If a team is undefeated, okay, we can use inductive reasoning to say they would keep winning. So this is the process of reasoning that a rule or statement is true because specific cases are true. So the past few days for our bell work, we've been working on that same packet, right? Could we use inductive reasoning to deduce that tomorrow we're probably still going to be working on that packet? Yep, okay, because there have been specific cases that we were working on it that would lead you to believe that would continue. Okay, so that's another example of inductive reasoning. Now, a statement that you believe to be true based on inductive reasoning is called a conjecture. Can you say another word that might be kind of similar to conjecture? No, because congruent means the same. Yes. A what? Conclusion. It's actually before you reach that. So a conjecture is going to be a statement that you think is true, right? Yeah? Hypothesis. Yes, a hypothesis. Have you guys talked about hypothesis in your science classes? Okay, so a conjecture is very much like a hypothesis, but this is a statement that is going to be based on your inductive reasoning, where with a hypothesis you would test that scientifically. Okay, so we're going to do the first one together. Okay, so let's look at the numbers. So we have 3, 6, 9, 12, and 15. So if I'm looking at these numbers, assuming that that pattern is going to continue, I want to figure out how I'm getting from one number to the next. Which, how are you getting from 3 to 6, 6 to 9, 9 to 12, 12
You're
to 15?
adding 3.
Okay, so you're adding 3 each time, right? Okay, so I would predict my next number would be what? 18. Okay, so Jay, why would we think the next number is 18?
Because the pattern is plus 3.
Okay, so then 15 plus 3 will be 18. Okay, so I put 18, and then if you're looking back at your notes, you can just put exactly what the pattern is. So the pattern is adding 3, so I just added 3 to 15. Okay, see if you can try the second one, which is a little different. Okay, so we have January, March, May. It's kind of very long.
That was on purpose.
Yep.
Oh, sorry.
That's okay. So find the pattern, right? That still isn't very good either. Okay, so Tony, did you figure out the pattern? Can you tell us what it is?
Every other month.
Okay, so January, skip February, then March, skip April, May. So then what is my next month? July. There it is. Okay, so now what we're going to do is we're going to complete this conjecture. So it says the product of 2 odd numbers is blank. So we're going to see, we're going to try to see if this conjecture is true or not. So the product of two odd numbers, we're gonna see if it's odd. I know, I think you guys are thinking, I saw some of you put even, I think you're thinking that because you're thinking of a negative times a negative is a positive. Okay, if you multiply 2, which is an even number, by anything, you're going to get an even number. Okay, so we're gonna complete the conjecture. And then let's show some examples. Okay, so I started with 1. 1 times 1 is 1. So 1 and 1 are both odd, and that's going to equal 1. Another example I gave was 3 times 3. That's going to be 9. Those are two odd numbers.
5 times 5.
Yep. And then they don't have to be the same number, right? It could be any two odd numbers. So then I did 5 times 3, which is 15. Okay, and then I want you to come up with 2 of your own. Okay, so any 2 examples of your own.
23.
Okay, now for the 2 that you're doing, are you getting the same result? Is the product still an odd number? Okay, so when you're doing this for your homework, instead of filling out this box first, you probably want to do the examples first, right? So start finding the product. When it says product, do we know what that means?
Multiplication.
Yep, it's the result of a multiplication problem. Avery, please don't do that. So you would want to find the product of 2 odd numbers, and then you can make a conjecture from there. All right, so to show a conjecture is always true, you must prove it. Okay, to show a conjecture is always true, you must prove it. To show that a conjecture is false, you only have to find, what do you have to find? We talked about this earlier. Before that. Remember, if it shows that it's false, what's it called? Xavier told us earlier. Counter example. Okay, and so you only have to find one example in which the conjecture is not true, and that is called a counter example. Okay, so you only have to find one example. So you only have to find one case, one instance where that's not true, and we know that the entire conjecture is false. And that one example that you find is called a counter example. So for one situation, there are usually many counterexamples. Okay, so you might not necessarily have the same counterexample as the person next to you. And that's fine. Okay, so for our first example, it says show that the conjecture is false by finding a counterexample. Okay, so let's look at the first one. It says for any real number x, x squared is greater than or equal to x. Now when you're doing this, you're probably going to have to do some trial and error. Okay, so if it's any real number, it's really any real number you can think of. When I'm trying to find a counterexample, I try to pick a positive number, 0, and a negative number, because usually it's something in one of those 3 categories. Okay, so I'm just going to write some work down on the side because we're going to try to find this. So for any real number x, x squared is greater than or equal to x. Let's pick a positive number. Why don't you guys throw one out? Yeah.
1.
Okay, so let's do 1. So if we have 1 squared is greater than or equal to x, so we're trying x equals 1. Sorry, you guys probably can't see 1 squared?
One.
1. Yep, no, that's okay. So 1 is greater than or equal to 1, is that true?
Yeah.
Okay, so if it's true, I usually put a little check. So if it's true, it can't be a counterexample. What if I plugged in 0?
That would be 0.
If I plugged in 0, I'd have 0 squared is greater than or equal to 0, which is still 0, right? Wouldn't that be true as well?
Yup.
Okay, so then I'm going to try a negative 1. Okay, so if I plug in a negative number, negative 1 squared is greater than or equal to negative 1. What would I have for that?
1.
I'd have 1 is greater than or equal to negative 1. So would that work? Would that be true?
Yes.
Okay. Okay, so then we could try what? We could try a decimal or a fraction. Okay, so this one was true, so this one wouldn't work. Do you guys want to try 1/2?
Yes.
Okay, so 1/2 squared is greater than or equal to 1/2. I'm sorry. When you square 1/2, do you guys know what you get?
1/4.
1/4, because it's 1 squared over 2 squared. So 1 squared is 1, 2 squared is 4. Is 1/4 greater than 1/2?
No.
No, because right, if you're thinking of fractions, a quarter is going to be less than half. Okay, so this would be your counterexample. So your counterexample would be x equals 1/2. And you would show me this. And then if it's not true, you just put the little line between it, saying, nope, not true. Okay, so this is false. Okay, so now we're going to try number 2. So it says supplementary angles are adjacent. So you're going to draw a picture. Yeah, I would draw a picture. Can you draw a picture of supplementary angles that are not adjacent?
This is true. No. You cannot.
Wait, does it only be 2 angles? Or can you put 3? You put 3.
Okay, now if they are adjacent, right, then they're right next to each other. So this would be true, right? This is not a counterexample. Thank you. Okay, so these are adjacent, right? So I have to try to draw 2 angles that are not adjacent but are still supplementary. And really, you could give these whatever you want to say. This was 130. And this was 50. And there are a couple different ways that you can draw your counterexample. So one way is just to draw them separately. Okay, so let's say this is 110, and this is 70. So they're not touching each other, but they're not adjacent. Okay, so if they're supplementary but not adjacent, then this is a counter example. So sometimes your counter example is just gonna be a picture. Did you guys draw some other pictures too? Okay, there would be another example. Okay, so they just cannot be adjacent, which means they do not share the same side and a vertex. So another way you can think of a counter example, sometimes you'll have like if-then statements, or you'll just have a statement. The first part of this statement has to be true. The second part has to be false. Okay, so for the first one we did, it has to be a real number. That has to be true. But x squared is greater than or equal to x. That has to be false. For number 2, what part of this had to be true? The angles had to be supplementary, right? But what part had to be false? That they were adjacent. So the first part has to be true, the second part has to be false. Okay, so sometimes it'll be written as a if-then. So if blank happens, then blank. We say this part has to be true, and then you have to show this is false. Okay, so for this one, x has to be a real number. For this one, the angles have to be supplementary. And then x squared should not be greater than or equal to x. The angles should not be adjacent. I'll zoom in so you guys can see that better. Okay, so whenever you have a counterexample, one part has to be true, and then you'll prove that the second part is false. All right, and then I'm going to give you the rest of the time to work on your homework, which is right at the top there.